And so in that case, H would be G alpha, and this would tell me that H alpha beta is G alpha beta, then H alpha beta would be G alpha beta. And so H alpha beta is the inverse of H alpha beta, and you can find that in the Polyakov action minus d to sigma Polyakov again, this is minus 2 by 2 square root of minus g times H alpha beta, G alpha beta, and if this is H alpha beta, this is delta alpha alpha, and this is equal to 2. So this is then equal to 2. This is just t minus t square root of minus h, and this is so you again recover the Namu-Koto action. So this is just to tell you that classically these two actions, Polyakov action and a Namu-Koto action, they are both classically equivalent. Now we let me first before I go to the symmetries, let me first prove what I have just said. Okay. So let me consider the Polyakov action minus p by 2 into sigma square root of minus h, and then or this, let me just call it h dot g, and now let me vary the variational. Let us make use of the variational principle to this. So what you have is delta s is minus t by 2 due to sigma into square root of minus this plus here let me write h dot g. Okay, and as you have in gravity theory, this delta of without its derivation, let me just write its value minus 1/2 square root of minus h alpha beta delta h. just what you do in general relativity, delta of the square root of minus g. Right? In gravity theory, you very often read this. Okay, and this is minus 1/2 square root of minus g alpha beta delta g alpha beta. Okay, just from general relativity, without going into the detail, I use this expression, and then you put both of them there, and then so I have minus d by 2. I can make one step, cut on one step. So d2 sigma square root of minus h delta h alpha beta, I take common. Then this is gone, this is gone, this is gone, this is gone. So I have here g alpha beta from here. Now from here, I have this is gone, this is gone, this is also gone, this is also gone. So I have just minus. Am I missing one point here? H or this is okay. H alpha beta is here. Please just check that I have not made any mistake. This from here, this is gone here. Delta H alpha beta is gone here. H alpha beta comes here, and H dot G comes here. Okay. What about this factor of minus 1/2? Oh, there is an extra factor of minus 1/2 here. There was one, this is minus t by 2. There is one extra minus 1/2 here. So this is correct. Okay, because it is going to be used at many places in the future, the definition of t alpha beta. And from here, we now define or construct this to be equal to t alpha beta. Okay, let us call this object as t alpha beta inside the rectangular bracket. And then what you have is d2 sigma t alpha beta, where t alpha beta is your.
Okay, so you defined it to be T alpha beta.
This I defined as.
No, G alpha beta.
Sorry. Thank you. Huge mistake. You can do that. Yes, it's very easy to make blunders in life. Yes. Okay. So this is T alpha beta. All right. And at many places you will find this as the defining defining thing, that delta S is delta S delta H alpha beta, delta H alpha beta, keeping delta H mu fixed, keeping delta X mu at 0, so keeping other variations as fixed is, and this H equal to minus t by 2 d2 sigma square root of minus h t alpha beta, or in some literature, you might find this as the definition for T alpha beta. What actually happens, this energy momentum tensor T alpha beta, it measures the response of S with respect to the metric variation delta H alpha beta, keeping all other fields unchanged. So this is one of the standard definitions that you find at many places. So I repeat that the T alpha beta measures the response of S to the metric variation with respect to the metric H alpha beta or that delta H alpha beta, keeping all other fields fixed, which means delta X is equal to 0. And this is what you exactly obtained here. You see what you have done here. You have varied the action with respect to what does it mean? It means you have assumed that the variation with respect to x mu is 0. Okay? Without saying that, if I write it like this, otherwise I should also vary. I should also vary it with respect to x mu, but assuming that delta x mu is 0, so I keep x mu